Okay, thank you, Javier. But at first, I apologize for change of my title because already 1 year has passed since I submitted my previous title. So today, I decided to talk about chirality in this phonon dispersion problem, a non-centrosemic micropolar crystal. So sorry, but this is not chiral magnetism, but chiral phonon problem. But however, what's behind is quite, let's say, common in both magnetism and phonon problem. Okay, so my collaborator is, as usual, so Alexander Vuchnikov and our young collaborator, Alexei Tereshchenko. And this talk is based on this PR paper published last winter. So today, I again apologize that my talk will not touch on nothing about magnetism, but phonon problem. Okay, and what truly chiral phonon? And second, I will talk about effective field theory of chiral phonon problems, so-called micropolar elasticity theory. And third, I will talk about experimental detection of chiral phonon. Okay, so the fundamental query is how lattice waves see chirality. So in words, how to say, a program of chirality touch all fields of condensed matter, including electron and spin and lattice wave and everything. So in that sense, how chirality affects the physical degrees of freedom is like a big interest for us. So in this respect, the phonon problem is also quite interesting for us. So today I will raise a fundamental query, how lattice waves or phonons see chirality. Okay, so this is the prototypical example of the phonon in chiral crystal. So maybe I think this is the simplest example. So the tellurium crystal. So tellurium is a chiral semiconductor whose space group is like this, P3121 and P3221. So an antiomorphic space group or there, like this. So left-handed and right-handed helical structure of tellurium atom is like this. And top view is like this. And the brilliant zone of this crystal is like this. Okay? Now, so how about a phonon dispersion along the z-axis? This is like a textbook like the issue. Let us see the phonon dispersion along the gamma A line. So this gamma line exactly corresponds to the chiral axis. In a real space chiral axis. In a momentum space, in brilliant zone, there's a gamma A line. Okay. So let's see at first the gamma point. So wave number is 0, 0, 0. Then in this simple tellurium case, a 3-mode degenerate like this. However, if we enter on a finite K area, so this 3-fold degeneracy is listed. And the 3 irreducible representation appears, delta 1, delta 2, and delta 3. Okay. And finally, at the brilliant zone H, like this. Of course, this information had been well known much before, like almost a half century ago, like this. But now let us have another look of this dispersion. Okay. So how chirality, concept of chirality enters here at gamma point 0, 0, 0. Yeah, so one longitudinal mode and 2 transverse mode exist here, but 2 transverse mode means just rotating mode like this. Just rotating, not propagating, because k equals 0, 0, 0. Yes? So this is just rotating. So just rotating degrees of freedom are never chiral. In terms of Lorentz-Barons, the definition of chirality. According to the Lorentz-Barons definition of chirality, rotation must couple with translation. This leads to a time-even pseudo-scalar physical quantity. Now, this situation happens on a delta line where k must be finite. Then, actually, three modes are not degenerate here, and there are the delta 2 and the delta 3 modes are like this. So delta 2 mode is this left-handed and delta 3 right-handed, and both phonons propagate along the crystallographic chiral axis like this. So this is truly chiral. Okay, so on the other hand, from group theoretical viewpoint, so delta 2 mode and the delta 3 mode are classified according to the irreducible representation of point group C3 along the delta line like this. Then, so the problem arises how to label the L and R left and right chirality. Okay? Then, so the answer is so-called pseudo spin angular momentum coming from discrete rotational symmetry is the answer. So discrete rotational symmetry means that this triangle here, yes, discrete triangle. So this triangle has C3 symmetry. So actually, irreducible representation of C3 point group gives you a gamma 2 and gamma 3. This gamma 2 and gamma 3 exactly correspond to delta 2 and delta 3 respectively. This coming from discrete rotation here. Yes, this is very important. Then, the new problem for our theorists arises how to describe dispersion of the truly chiral phonons. The problem itself is quite simple. How to describe these modes by using a effective model. Yes? The question itself is quite simple, but the answer is not so simple. Yes. We must, attack this problem using not group theory classification, but dynamics needed. Yes. So this is just group theory classification. Oh, delta 1, delta 2, delta 3 are there. But what about the chirality enters here? How chirality enters here? How angular momentum enters here? Yes, so group theory cannot tell you about that. So to think of this, we need dynamical theory. Dynamical theory means that we need effective effective theory, yes, which theoretically describes the whole structure of phonon dispersion. Yes. Then, so we enter the theoretical frameworks. At first, let's try to start with usual conventional elasticity theory like this so-called quasi-elasticity theory. Yes. So usual elasticity theory consists of strain tensor like this. However, this strain tensor includes only polar vectors, yes, displacement and position vectors are both polar. So there is no chance to create any pseudo-scalar. Yes, this is like a dead end. So how to overcome this difficulty is our next problem. The answer is let's introduce an axial vector field. So this framework is realized by using a micropolar continuum field theory, which saves us. So what a micropolar continuum field theory? So the essential point is not so difficult. Yeah, so any second rank tensor can be decomposed into the symmetric and anti-symmetric parts like this and like this. However, when you write this, yes, omega k, a rotational part dependent on u, yes, then, so yeah, this rotation cannot enter the energy density. This is quite a well-known fact in elasticity theory. But let us observe that this Cauchy strain tensor can be written like this. Yes, here still omega appears here. However, let us promote this omega field to an independent local field phi like this. Let us elevate omega to independent. Not a dependent, but independent field like this. Okay? This is the essential point of this theory. Yes? So by introducing this rotational field, we can construct micropolar, so-called micropolar continuum field theory, which was developed by Seymour Ellingen in a context of mechanical engineering. Okay. So in summary, so we can attach both the polar field and the actual rotational field on each point in a space like this. So then we have two independent strain, generalized strain field. First, micro deformation tensor like this, and second, so-called Linus or micro rotation tensor like this. Then we can construct energy density by using this epsilon and gamma tensor field like this, and epsilon, gamma, gamma, and epsilon, gamma. Then we are enough lucky to have this chiral term like this. This chiral term is coming from the epsilon and gamma. So this naturally becoming a time-even pseudoscalar. Yes, this is a truly chiral term. So we are very happy with this term. So then we can, we can construct the equation of motion for elastic deformation like this, and I will skip the detail like this. And we go further. We need to specify the point group symmetry of crystal, which we are considering. So let us take 6Q2, this 6-point group. This point group exactly corresponds to the chromium niobium disulfur compound, which Kosaka-san heavily mentioned in his talk, in my previous talk. Yes. So we take up this 6Q2 point group. Then I will skip the detail, but anyway, we can construct the equation of motion for displacement and rotational field like this. And what's essential ingredient? So the diagonal part is there appears k-square term. This is just like a usual phonon mode, acoustic mode here. But here, yes, in this another diagonal part, here appears Jaroszynski-Moria interaction like term here in the phonon. Yes. So this coupling term consists of k-linear term. Yes. So the k-linear coupling means just like Jaroszynski-Moria interaction. Yes. So the this part, this coming from the pseudoscalar term that I mentioned before. Yes. So and also there appears the off-diagonal part here. Yeah, this off-diagonal part component means hybridization between translational and rotational mode appears here. Yes. Then now what we need to do is rather straightforward. We simply solve this equation and draw the dispersion curve. Yes. Okay. So as a result, we consequently we obtain this dispersion relation. So let us have a look. Oh, here, this red line is transverse right. Yeah, right-handed chiral, and the blue one left-handed, and this dotted one is longitudinal. Yes, and another transverse right and transverse left appears. So what the most important is that there appear splitting of phonon modes depending on their chirality. This is truly chirality-induced effect, like this. Okay. Now, please compare this figure with the group theory-based result here. So it's quite how to say natural to observe that delta 1 corresponds to longitudinal mode and delta 2 corresponds to blue one and delta 3 red one, like this. Yes. So now we say that we successfully describe these group theory-based modes using effective micropolar continuum field theory, like this. So finally, I will briefly mention some recent topics. Yeah. These are, for examples, our, how to say, materials like this. So like this, yes. Then, quite recently, I collaborated with experimentalists, and we made Raman, circularly polarized Raman spectroscopy. Yes. Sorry. Raman spectroscopy. Yes, like this. So by doing Raman spectroscopy on HGS, so-called cinnabar crystal. Yeah, cinnabar crystal. So this is also the chiral crystal. We successfully observed the chiral phonon model. And what's new? What's new is that we successfully assigned angular momentum to each phonon model. 0, +1, and -1. Yes. And here I describe how we can assign so-called pseudo-angular momentum to each dispersion. So we quite recently we submitted this paper, and we are supposed to put this paper on Condomat archive. So I hope if you have some interest, please visit the archive and find out our paper like this. So I described how to define pseudo-angular momentum here. Okay. So now time is running. So I show you the how chiral phonon look like. So this is the pseudo-angular momentum +1. So this so let's enjoy this movie like this. So we can clearly see that there's some rotation together with the translation coexist here like this, And the pseudo-angular momentum 0 case is like this. Next one is top view like this. This is PAM, pseudo-angular momentum is +1 and -1, and this is 0. Yes. So we could successfully assign +1 rotation and -1 rotation and 0 rotation. So this exactly corresponds to these, how to say, these bottom three mode. Of course, Raman spectrum cannot detect how to say, lowest mode. So the upper finite energy mode. Yes. Yeah. However, anyway, we consistently assign the angular momentum of phonons to each dispersion. Yes. Okay, so I summarize my talk, and we have established the micropolar continuum field theory to describe chiral phonon. Yeah, that's established. So based on this continuum field theory, we can describe phonon mode in a given crystal. If you specify point group, we can get dispersion curve by solving the equation of motion. Yes. Of course, this theory is based on a continuum field theory, so miss the discreteness of lattice. So how to connect our continuum field theory to discrete lattice case is like a future problem. And now we are elaborating on this problem now. Okay, so this first part has already been published, as I mentioned, this paper, together with Sasha Ovchnikov and Alexei Tereshenko. And as for the second topic, the experimental detection of truly chiral phonon, yes, in tellurium and cinnabar. We recently submitted paper. The paper is supposed to appear in archive Condomat. Okay, so thank you.
Did you in the second subject?
Yes.
Did you compare your continuum results, your theory done in the continuum with the things that you can do by using the isotropy code or the Bilbao crystallographic server, both codes, both.
Yes, exactly. Yeah, we did. Yes. Yeah.
Bilbao. Bilbao and also the code in Utah University.
Yes.
For this to describe these things.
Yes. Actually, we use the Bilbao server and assign the illusory representation based on the Bilbao style. Yes.
Because I think that's also the isotropy code from Harold Stokes, Branton Campbell. They also have very good utilities to think on this kind of phonons, etc. Maybe you can have a look on this.
Okay, thank you, sir. Yes.
Thank you very much, John. Then